All right, this is exercise 5 from section 5.2. So we're given a pair of functions here. Function R represents basically the tide removing, the rate at which the tide removes sand from a beach. And function S represents the rate at which a pumping station puts sand back on the beach. So we're told both of these are measured in the same rate, cubic yards of sand per hour. T is measured in hours, and these functions are valid over a 6-hour span of time. So, A, what definite integral measures how much sand the tide will remove during that time period? So only one of these functions talks about the sand removed during the tide. So if we want to know how much sand is removed, we want to integrate, basically we want to accumulate over this rate of change. So I want to integrate the rate of change function with respect to time over the time period that I actually care about. So in this case, I am told that I want to know how much sand is going to be removed over that time period from t equals 0 to t equals 6. So I'll represent this a couple of different ways, really. But for one of these, I'm being really explicit about what R of t is. Okay. So this is the integral that gives this, and I think I explained why that's the case, but I'll remind you of kind of what my reasoning is, and maybe I'll give you a graphical representation too. So this function right here is a rate function, and this rate is given in cubic yards per hour. So, and I want to find how much sand will be removed. So that's going to be a volume, not a rate of change of volume, just a volume of cubic yards. So let's say I had a graph. I'm not going to try to graph this function at all accurately, but what I want to show you is, what this area would be. So this rate is given in cubic yards per hour. The time is given in hours. So if I were going to integrate this by finding the area underneath this curve, what would that product look like? Or what would that product have units of? Basically, I would model this with rectangles if I were to think about it in terms of Riemann sums. And those rectangles would have areas that are, in the dimension of hours times cubic yards per hour, which gives me what? That gives me cubic yards. All right, so moving on to part B. Write an expression for y of x, the total number of cubic yards of sand on the beach at time x. So this might sound like actually, no, I was going to make an assumption, but let's not do that. So write an expression for y of x, total number of cubic yards of sand on the beach at time x. So we're given two different rates here. One of these rates talks about how much sand is removed from the beach, and the other one talks about how much sand is added to the beach. So those are rates that are kind of opposing each other. So if I want to find the rate of change, or like the total change of sand on the beach at any time, I'm going to integrate from, actually, let's not put the limits or the limits of integration in yet. So at what rate is sand being added to the beach? That comes from S of t. So I'm going to integrate S of t, and it's being removed at the rate of R of t. So I'm going to integrate the sum of these functions with respect to t. But what I want is an expression for y of x. which is the total number of cubic yards of sand on the beach at any time x. So basically, I have an accumulator function. So I'm going to accumulate from time 0 whatever time x is. So basically, we had a previous homework question like this where we had a function that was defined by an integral, where basically the input to this function gives you the upper limit of integration of this integral. Right, but is this enough? Does this integral give me the total number of yards of cubic yards of sand on the beach? Not exactly. What this integral will give me is the total change in the volume of sand on the beach. But what it doesn't incorporate is whatever the initial amount of sand on the beach was. So that is going to come from, actually, let me write this one more way. This integral from 0 to x, by the fundamental theorem of calculus, what this gives me is y of x minus y of 0. So if I want to find y of x will be equal to y of 0 plus this integral I just wrote down. Do I know what y of 0 is? Well, y of 0 represents the amount of sand on the beach at time 0. I actually do know that. That is given to me as 2,500 cubic yards of sand. That was an initial condition that we were given. So this function right here is a variable function. I can basically plug in any value of x, and this integral will give me, or basically this expression, including that integral, will give me the total amount of sand on the beach at any given time. All right, part C. At what instantaneous rate is the total number of cubic yards of sand on the beach at time t equals 4 changing? Okay, so I want an instantaneous rate of change of some function. What is that function? That's a function that describes the total number of cubic yards of sand on the beach at any time. Well, that's a function we just wrote. That's what y of x is. So let's borrow it. We know that y of x is equal to 2,500 plus the integral from 0 to x. Was it, should be s minus r, right? S minus r of s of t minus r of t dt. Okay. I want to find the instantaneous rate of change of this function. So let's do that first. I want to find the derivative. So what is y prime of x? Y prime of x will be equal to, well, the derivative of 2,500. That's going to be 0 because 2,500 is a constant. But what about the derivative of this integral? So let's invoke the fundamental theorem of calculus here. I know that s and r are both continuous functions, which means they have integrals. Let's say this. Let's give names to the antiderivatives of these functions. The derivative of, I don't know, what letter is a good derivative for s? Let's say the derivative of p is s of t, and let's say the derivative of q of t is r of t. So I don't need to know what those, like how p and q are defined. I'm just giving them names. So actually, let's throw a step in here. Let's say y of x. Now that we've given names as antiderivative, let's do this. Y of x equals 2,500 plus, what does the fundamental theorem of calculus say? Well, the integral of some function s of t from 0 to x is going to come from its antiderivative evaluated at both endpoints. So that's going to be t of x minus P of 0. And then if we do the same thing for R, that integral is going to be Q of X minus Q of 0. Let's clean this up a little bit. We get 2,500 plus P of X minus P of 0 minus Q of X plus Q of 0. Okay, so maybe you're asking why I brought in all these terms. Basically, I'm kind of showing why the fundamental theory, or another way the fundamental theory of calculus works the way it does. Really, I wanted an instantaneous rate of change of y, so let's take a derivative now. What is y prime of x? A lot of these things are going to go to 0 because 2,500 is a constant, so it becomes 0. P naught, or P of 0, I don't even know what the definition of this function P is. But I know if I evaluate it at like a definite value T, that'll go to 0. Same with Q of 0. But what I really have is y prime equals P prime of x minus Q prime of x. What is P prime? Well, by our definition here, the derivative of P is S of T. So y prime of x equals S of x minus Q prime of x, which is R of x. So, and this is kind of what the derivative of what one of the consequences of the fundamental theorem of calculus is that derivatives and integrals are inverse functions of each other. So what's the derivative of the integral of S of t minus R of t from the interval from 0 to x? That becomes S of x minus R of x. And now that we have that, we can evaluate this derivative at x equals 4. So y prime of 4 equals S of 4 minus R of 4. Let's go ahead and evaluate this function at both those values, or these functions at those values. So 15 times 4 over 1 plus 3 times 4 minus R of 4 minus 2 plus, oh, I should really capture this whole thing. 2 plus 5 sine 16 pi over 25. So let's get an approximation of this. So 60 over 13 minus 2, 26 over 13 minus 5 sine 16 pi over 25. And give me a second to go to the calculator. Getting negative 1.91. So what did we just find numerically? So basically at this time, sand is being removed from the beach at what rate? So it's being removed at a rate of 1.91 yards cubed per hour. All right, moving on to part D. All right, over the time interval 0 to 6, at approximately what time t is the amount of sand on the beach least? Okay. So we want to find the minimum of a function. What is that function? Well, that function should be y prime, or so it should be y, right? Because y is the function we built, which talks about how much sand there is on the beach. So what I want to do is take the derivative of that function and set it equal to 0. So where will that derivative be equal to 0? Well, what is the derivative of y? We said it was s of x minus r of x. So this is equivalent to saying this. S of x minus r of x equals 0. If the difference of these two things is 0, that means that s of x equals r of x. So when's that going to happen? So I have 2 plus 5 sine of 4 pi x over 25 equals 15x over 1 plus 3x. This is not something I would expect anybody to try to solve by hand. I think that actually might be impossible. So let's do this. Let's let Desmos give us a look. Bear with me while I graph this on my other monitor, and I'll show it to you. 2 plus 5 sine 4 pi x. Y equals 15x over 1 plus 3x. All right, here's a strange looking paragraph. But what did I really care about? I cared about where these functions are equal to each other. So that's going to happen at approximately, are you giving me a crossing point here? So with zeroing on it, well, let me take a different approach to this. They're going to be equal wherever their difference is 0, right? So maybe I'll just look at it like that. I think I can trust Desmos to give me an x-intercept. There it is. So I would say at approximately t equals 5.118, we're going to see a minimum, or we're going to see a critical point at the very least. All right, and that's all for this question.